In this set of notes, we're going to look at a review of some introductory statistics concepts. If some of the topics you haven't seen before, no need to worry. We're just going to kind of do an overview of them right now, and then as we need them throughout the semester, I will come back and review. So we're going to start out with the idea of the parameter versus the statistic. This is one of the most fundamental concepts. Researchers are often interested in learning about some group of people or things, but that group, unfortunately, the researcher cannot collect data from every unit in that group. So since we cannot collect data from the entire group of interest, and that entire group of interest is what we know as the population, we are forced to look at some subgroup and collect data from that subgroup. And so this subgroup, or this smaller group from the population, that is what we call the sample. All right, so we've got a couple definitions here. The first one is what is being measured, and that's what we call the variables. The individuals that we measure, those are what we call the subject or the unit. Our next definition is population. The population is who or what we want to learn about or examine. Most of the time it's a large group, but it doesn't necessarily have to be. So as a researcher, you really want to think about who your population is and be specific. So for example, are you interested in all adults? So that would be all adults worldwide. Are you interested in all adults in the United States? Are you interested in all adults in the state of Kentucky? Are you interested in all adults in Fayette County? Are you interested in all adults who have coronary heart disease? You want to be as specific as possible. And the reason for this is the more specific you are about who your population is or who you're actually interested in learning about, that's going to make your data collection easier. Our next definition is sample. So the sample is the set of individuals, items, or animals selected from the population. And once the sample is selected, we collect and we analyze data. Now, the only reason we collect a sample instead of looking at the whole population is because looking at an entire population is often impossible. If it ends up that you are able to get population data, then you want the population data. You don't want the sample data. We only collect the sample because we cannot inspect the entire population. Our next definition is parameter. So the parameter is the specific piece of information we would like to learn about the population. If we can't collect data from the entire population, then we don't know the value of the parameter. In other words, we know conceptually what it is. So for example, it could be the average BMI of all people who live in the state of Kentucky. That number exists, but since I can't find the BMI for all adults who live in the state of Kentucky, I don't know what that value is. So conceptually I can say what it is, but I can't say what the exact value is. On the other hand, the statistic, that's going to be an estimate of the piece of information we would like to know about the population, but we calculate it from the sample. So if I have 100 randomly selected adults, all who live in the state of Kentucky, and I find the average BMI for those 100 adults, and notice this is something that would be feasible, I could do this, I would actually know the numeric value of the average BMI for that sample. And then the whole idea is if I know the average BMI from that sample, is there a way that I could then extend that information to say something reasonable about the parameter, in this case the average BMI of all adults living in Kentucky? Next, we're going to talk just a little bit about probability and random variables, and this is the piece that it's likely you didn't see in your intro course, and that is perfectly fine. We're just, again, going to kind of do an overview here. So thinking about one of our main goals is we want to be able to use that information from part of the population, i.e. the sample, to draw conclusions about the entire population. We can never be certain that those conclusions we reach are correct. Probability is the science of uncertainty, and what it's going to do is it gives us a way to describe the values that a variable may take before we take any measurements. So for example, before administering a diagnostic test, we may want to know the probability that a patient with a disease will test positive for the disease. So probability gives us ways to answer questions like this. It also gives us a way that we can use the information in the sample to eventually say something about the population. So most of the inferential methods that you learned about in your intro stat class, there are actually probabilistic underpinnings for all of those. So like if you kind of look under the hood of all those inferential procedures, you would find some probability. So starting out with some definitions, we say that a process is random if the outcome of the process is unknown before it occurs, but the possible outcomes follow a regular pattern in the long run. So for example, consider rolling a die. Before throwing the dice, and we'll say that it's a 6-sided die, you don't know where it's going to land, but you do know if it's a fair die that there's a 1 in 6 chance of seeing any of the particular faces. So you know if you've got a 6-sided die, if you roll it, there's no way you're going to see a 0 or a 100 or a 7 or a million. You know what the possible outcomes are. There are 1 through 6. And if it's a fair die, you know what the probability of each of those are. An event, on the other hand, is an outcome or set of outcomes of a random process. And we generally denote events with capital letters. So for example, if we're interested in the event that the die lands on an even face, we could say something like the following. We could say capital A is equal to the die lands on an even face, which is equal to the set of numbers 2, 4, and 6. The sample space of a random process is the set of all possible outcomes, and we usually denote it by capital S. So for our dice example, S would be equal to the numbers 1, 2, 3, 4, 5, and 6. And then finally, the probability of an event is the proportion of times the event would occur over time. So probabilities are always going to be between 0 and 1. If you'll remember back to your intro stats course, remember that p-values for hypothesis were always between 0 and 1. This is because p-values are really probabilities. So for example, if we roll a die an infinite number of times, I expect, that should say the die, to land on the number 3, 1/6 of the time. So we could write the following. We use capital P here and parentheses to denote probability. So this piece right here would read the probability that the die lands on a 3 is equal to 1/6. The probability that event B occurs, given that event A occurs, is what we call a conditional probability. And it is denoted by P, B given A. So this reads the probability of B given A. So if we think about what that notation looks like, the P stands for probability, and that is with those parentheses. That vertical line there, means given, and then we've got our two events right here. So we have what's called the conditional probability rule. And it says the following. If A and B are any two events with a probability of A being greater than 0, then the following holds true. If you can find the probability that A and B occur together and divide that by the probability that A occurs by itself, that will give you the probability that B occurs, giving A has already occurred. We could solve here for probability of A and B. Notice we do that by multiplying both sides by the probability of A, and that gives us what we call the general multiplication rule. And what it tells us is if I know the probability of A occurring and I know the conditional, then I can get the probability of both of them occurring simultaneously. And our last little bit of probability we're going to talk about is independence. This is one of the most important concepts in probability. And so what we say is that event B is said to be independent of event A if the probability B occurs giving A has already occurred is equal to the probability of B. Don't get too lost in the notation here. Essentially what we're saying here is since these two are equal to one another, conditioning on A gives no extra information about B. So if event B is independent of A, then event A is also independent of event B. And then if they're not independent, they are said to be dependent. So again, that's just a little bit of an overview of some different probability rules. Don't worry too much about it if you haven't seen these before. I just want to have these out there so they have at least been mentioned, and then we can come back to them as we need them throughout the course. All right, next we're going to talk about random variables. So the reason a discussion of probability is important is before collecting the sample, we don't know what the value of the statistic will be, but we may be able to predict what is going to happen. We say that the statistic is random, again, because we don't know what the value is before collecting the sample. And more specifically, we can think of the statistic as a random variable. So a random variable is a numerical quantity resulting from a random process. There are two different types of random variables, just like there are two different types of variables, and you probably saw that in your intro stat course. There are discrete random variables, and there are continuous. A discrete random variable is a random variable whose possible values can be listed, whereas a continuous random variable is a random variable whose possible values form some interval of numbers. This is the same idea as continuous versus discrete quantitative variables that you've learned about in the past. The only reason we put random in front of here is we haven't actually taken any measurements yet, so we don't know what values the variable is going to take. Now, just like with when you talked about variables before, because there's a limit to the accuracy of any measurement instrument, such as a scale or a watch, it may seem that any variable should be thought of as discrete. However, when there is a large number of closely spaced values, we do study it as continuous. Generally, when talking about random variables, we use capital letters and we use lowercase letters to represent the actual values the variable may take. So for example, if we're interested in seeing the probability that a random variable x takes the value 2, we could write the following. Notice here we've got that probability notation again. So this reads, the probability that the random variable x equals 2. So this random variable piece right here in the sentence, that piece is in there because x is capitalized. If x were lowercase, we wouldn't have that piece of the sentence. So that's the distinction there between the capital and the lowercase that you'll generally see with probability notation and talking about random variables. So for each of the following, we're going to decide if the variable described is random, and if it is random, we're going to decide if it is discrete or continuous. So if you want to pause for, right now, see if you can answer these three, and then when you come back, see if you get the same answers that I did. All right, for number one, we're going to say that x is equal to a patient's systolic blood pressure. Now, prior to taking that measurement, there's no way for me to know what that patient's systolic blood pressure is going to be. So this is random, and it is continuous. y equals 0 if a child's parents are not married, or y equals 1 if a child's parents are married. Now again, prior to interviewing the child, I don't know if their parents are married or not. It could be one or the other. So this is going to be random. And then notice y can only take the value 0 or 1, so this is going to be discrete. Next, X, the current WHO recommended maximum daily sodium intake. Now, prior to me going onto the internet and looking this up, I personally don't know what it is, but it is a fixed number. It doesn't change. Once I know what that number is and I go and look it up again, it's not going to change. So this is not random. You know, this isn't going to change each time I go and look up that value. So that one's not random. All right, next we're going to talk about probability distributions. So a probability distribution is a mathematical model that relates the value of the variable with the probability of the occurrence of that value in the population. So you can think of it as a way to describe the pattern that the variable is going to follow. Different types of variables follow different types of patterns. So we need different types of distributions to describe them. And we're going to look at just a couple different distributions here. When we talk about the potential values the variable may take, we refer to it again as random, since we don't know what value it's going to take just yet. A continuous probability model assigns probability is the area under a density curve. For continuous probability models, we'll be interested in the probability of a random variable occurs within a range of values. The probability of a random variable occurring within a range of values is the area under the curve above the range of the values. And you have seen continuous probability models before when you looked at a normal distribution. A normal distribution is a type of continuous probability model. Now there are many other ones, so if you've heard of an F distribution, chi-squared, all of those are continuous. And so they all have the following properties. The total area under the curve is equal to 1. The proportion of the data in any interval is in that area over the interval. And the curve is always on or above the horizontal axis. So we're going to look at just a couple different probability distributions that you might see. The first one is called the binomial distribution. And so this one is going to be discrete. So we're often interested in the repetition of an experiment. So each repetition will be called a trial. And we're going to consider in this section the cases where each trial only has two possible outcomes. And so first we're going to define what is called a Bernoulli trial. So repeated trials of an experiment is called a Bernoulli trial if the following three conditions are satisfied. The experiment, each trial has two possible outcomes, denoted generically for success and failure. The trials are independent, and the probability of success, which we call success probability, and we denote P, remains the same from trial to trial. And so let's look at an example here. So in a certain population, 12% of people can be classified as being high risk for a heart attack. 3 people are randomly selected from this population. All right, so for this example, let's talk about what a success is. So a success would be if a person is high risk. So notice we only have 2 options here. They're either at high risk or they're not at high risk. So we have 2 options. So success is going to be the person is high risk. A failure would be they are not high risk. Are the trials independent? In this case, I would say yes. So notice we have 3 trials here. The reason we have 3 trials is we're selecting 3 people. So we're going to consider each of those people a trial. And during each of the trials, we're going to find out if that person is high risk or not. Now, we don't have any reason to think that the trials are not independent, and the reason for that is we have randomly selected these people, so it's very unlikely that they, for example, live in the same household, they're related to one another, so forth. Now, if we had any extra information that maybe said they were siblings or they lived in the same household, then they may not be independent. But for this particular example, we don't have any extra information that suggests that. We're going to determine the success probability. So notice there's a 12% chance that people are classified as being high risk for a heart attack. That means for each of the people that we talk to, there's a 12% chance that they are at high risk. So in this case, we say that P is equal to 0.12. And so the question is, are these Bernoulli trials? And the answer is yes. We have 3 different Bernoulli trials because we've met each of these 3 characteristics up here on the bottom of page 3. So in Bernoulli trials, the number of outcomes that contain exactly X successes equals what we call the binomial coefficient. And so this is the definition of the binomial coefficient. And what this reads as is N choose X. Okay. So what we're saying in terms of our previous example is if I have 3 people, how many ways can I choose how many ways can I choose X successes? In other words, how many different ways are there to have X people of high risk out of 3? And this formula will give you that answer. So for example, let's say that of our 3 people, we wanted to find out how many ways there were to have one of them be high risk. So we could list these out. So we could have the first person be high risk, and then the second person be not high risk, and I'll use an N there, and then the third person be not high risk. I could have the first person be not high risk, second person be high risk, the third person not, and then I could have not high risk. So notice there are 3 different possibilities. There's no other way out of 3 people that I could only have one of them at high risk. So if we fill this into our formula, if I have 3 choose 1, that's going to be equal to 3 factorial divided by 1 factorial times 3 minus 1 factorial. And so as a reminder, if it's been a while, 3 factorial is 3 times 2 times 1. 1 factorial is just 1. Then we've got 2 factorial, so that's 2 times 1. So notice here, that is 3, and that is exactly what we found up here. All right, so again, this is the number of possible combinations of X objects from a collection of N. From this experiment, we are interested in the total number of successes out of the N trials, and this is what we call a binomial. So this is the binomial distribution. So essentially what this distribution does, this formula, is this tells us the ways to choose the successes. The P of X, what it's doing is that is the probability of success multiplied by each of the successes, and we do this because they're independent. So this goes back to that idea of independence from earlier. So these are the probabilities for the successes. And then this piece, the 1 minus P, that's actually taking care of the probabilities for the failures. We're going to do one example of this by hand just to give you an idea of how this would relate or how this could be used, but most of the time we would just use a computer to calculate these for us. All right, so we're going to calculate some probabilities here. So we're going to use the formula to compute the probability that all were high risk. Well, we've got 3 people. So if they're all high risk, what we're doing here is we're looking at the probability that X, which is the number of successes, is equal to 3. Okay, so everybody's high risk in this case. So to do this, we fill in our formula. Out of our 3 people, all 3 are high risk, or we have 3 successes. Our probability of success is 0.12, so we're going to take that to the x, which in this case is 3, times 1 minus 0.2, and we're going to take that to the 3 minus 3 power, which ends up being 0. And if you put this in your calculator, you will find that this is equal to 0.0017. And then notice it says find the probability that no more than 2 were at high risk. So if we're finding the probability that no more than 2, that's the probability that x is less than or equal to 2. So notice that's the probability that x is equal to 0 plus the probability that x is equal to 1 plus the probability that x is equal to 2. So you would do the same thing that we did up here and fill in that formula. So I'm going to leave you to try that on your own, and I'll tell you what the answer should be. You should find 0.9983. Right? And I will, on your version, I'm going to move the Poisson distribution down to the next page so you've got some room to work that. All right, so next we're going to talk about the Poisson distribution. So the Poisson distribution is another discrete distribution. So in some situations, we want to consider rare events or events that have small probabilities. The Poisson distribution is similar to the binomial, but it's used to model the occurrence of rare events, and it can be used when the random variable represents the number of cases under 3 different conditions. And a very large number of independent Bernoulli trials when the probability of success is small, for a unit of time, and on a unit of area or volume. The big take-home here is Poisson distributions help us look at the probability of count data. So anytime you have count data, you're going to use a Poisson. And be careful here because the binomial almost sounds like count data because you've got a certain number of trials and you're looking at the number of successes out of those trials. Whereas a Poisson distribution, we're generally looking at a certain amount of time, and in an amount of time, how many do we count? Or in a certain area, how many do we count? Similar to the binomial up above, here is the formula. And so let's just apply this formula and see what we can find. So we're going to let x denote the number of new spina bifida cases in 1 month in Kentucky. Suppose on average there are 3 live births per month with spina bifida. And we want to find the probability that in a randomly selected month there are exactly 4 new spina bifida cases in Kentucky. So in other words, we want to find the probability that x is equal to 4. Now, if we look up here at our formula, notice that we also have lambda. So we need to find lambda. Lambda is what we call the rate parameter for the Poisson. It's always going to be what occurs on average. So notice here in our problem statement, it tells us that on average there are 3 live births per month. So what this tells us is lambda is equal to 3 for this particular case. So from here we can fill in our formula. And then if you put that in your calculator, you will find that that is equal to 0.16803. So that is that probability. We have about a 17% chance in a month in Kentucky of having 4 new spina bifida cases. These can be really useful because suppose that you're working for a hospital and you're trying to figure out how to prepare for certain things happening. Okay, so you want to prepare if you've got a certain number of patients with a particular condition. Are you ready to handle that? Using a Poisson distribution, we can figure out of what the probability of seeing those types of patients or the certain number of those types of patients within a given time frame. So maybe you're interested in patients that need the ICU, for example. If you know within a month what that average count is, you could use a Poisson distribution to potentially model how many patients you're going to have in a month. And if on average you have, however many, you can look at the probability of more than the average. And once that probability starts to drop off, then you don't need to prepare for that many more than the average. Now, doing something like that can be more complicated than that, but that's one way that a Poisson distribution could potentially be used. Find the probability that in a randomly selected month, there are at most 2 new spina bifida cases. So in this case, we would find the probability that x is less than or equal to 2. Now, anytime that we've got this less than or equal to, like we saw in this example and the one previous, this is what we call a cumulative probability. And just like before, notice this is equal to the probability that x is equal to 0. There are no cases, or there could just be 1 case, or there could be 2 cases. So try this on your own, and you should get 0.42319. All right, the next distribution we're going to look at is a continuous one, and it's the one that you're probably the most familiar with. It is the normal distribution. So again, it's associated with continuous random variables, and it's used to model many real-world phenomenon. I'm not going to spend too much time here on the normal distribution because I know that you've seen this one before, but here is a picture of some different potential normal distributions. Normal distributions are characterized by both their center and their spread, or their mean and their variance. The mean of the distribution controls where the center of the curve is, and the variance controls how spread out it is. So for example, if we can compare the red and the blue curve, they both have the same center, but the red curve has a much larger standard deviation or variance, and then the same could be said comparing to the yellow curve. The green curve, on the other hand, has a different center because it's centered at a different spot compared to the other 3 curves. One of the reasons the normal distribution is so important is because of the central limit theorem. And the central limit theorem tells us if y1 through yn are independent random variables with mean mu and variance sigma squared, then we know that the distribution of the mean approaches a normal standard 1 distribution. So you've seen this before anytime you heard about a standard normal distribution. Typically, we use the rule of thumb that our sample size needs to be bigger than or equal to 30 as our criteria for a large N. This is again when we're working with means and we're applying the central limit theorem. But sometimes you may need your sample size to be much larger. And then also if the y's are identically distributed and that distribution of each y does not depart radically from normal, then we could go as low as 3 or 4 and the central limit theorem will still hold. And then it ends up that for any sample size, if the random variable we're working with is normally distributed, then if we look at the mean of those random variables, that mean is going to be normally distributed with mean mu and variance sigma squared over n. And then for very large sample sizes, even if our random variable we're interested in is not normally distributed, we see something very similar. All right, the rest of these here, these sections, again, I'm just going to very quickly mention them because you should have seen these before in your IntroStat course and be fairly familiar with them. We have the sampling distribution. We will talk more about sampling distributions later on in the course. It is the distribution of sample statistics computed for different random samples of the same size from the same population. The reason we care about sampling distributions is it gives us a way to help describe the behavior of the sample statistic and how that statistic varies from sample to sample. Once we have an understanding of that sampling variability, that's what's really going to allow us to build statistical inference and be able to say reasonable things about the parameter based on the value of the statistic. So we have confidence intervals. If you remember what a confidence interval is it allows us to take the information contained in the statistic, we can compute an interval around that statistic, and that interval gives us a range of plausible values for the parameter, which is what we're really interested in learning about. And then finally, we've got hypothesis testing. It gives us a way to answer a question about the location of a parameter utilizing the information from a statistic. And so one of the key concepts in a hypothesis test is this idea is that there's some real truth that's going on in the population. And so we split the hypothesis test into the null and the alternative. We don't know where the parameter is for sure. The parameter could be in the null or the parameter could be in the alternative. So one of these up here is the truth. Based on the information contained in the statistic, we're going to make a conclusion about the parameter, or about the hypothesis, which tells us something about the parameter. We're either going to fail to reject the null or we're going to reject the null. So these are the test conclusions. And we hope one of two things happens. Either the parameter is really in the null hypothesis and we fail to reject that, so we get it right, or the parameter is in the alternative and we reject the null. Either of these scenarios we're happy, the correct thing happened. But since there's no way for us to actually know what's going on in the population, there's always that possibility for error. And so we always want to be transparent about that. And so there's two types of errors we could make. There is the type 1 error and there is the type 2. And there's just a little bit of notation down there. Again, this note set was just meant to be a flyby of some introductory concepts. It wasn't meant to be very detailed at all. As we move forward and we start introducing new things, the pace will be much slower than this note set and much more detailed. If you have any questions about this, please let me know. You'll see the quiz for this note set is really just, did you get the main ideas, not necessarily the details.